Okay, good morning, everyone. I hope you had a nice weekend. And we start today section 11.10, Taylor and Maclaurin series. All right. In the previous section, we found the power series representation of a lot of functions. And we did that by basically manipulating the geometric series. So everything we did was based on the geometric series. So when we started with 1 minus 1 over 1 minus x, and that's 1 plus x squared plus etc. That was based, that's the geometric series. That's how we got 1 over 1 minus x. And everything was based on it. So when we found 1 plus x, it was based on 1 over 1 minus x. When we found ln of 1 plus x, we just integrated this one. So it was based on the geometric series. When we found arctangent of x, again, we integrated 1 plus 1 over x squared. And this again was based on the geometric series. So far, every power series of function, we did it based on the geometric series. So the question is now, what about other functions? There is no way we can relate them to geometric series, like sine x. How can I write this as a power series? Cosine x. How can I write this as a power series? Which I've always emphasized that basically we're writing them as kind of polynomial with infinite degree. Cosine x the same. How can I write cosine x as power series? Those I cannot connect them. Cosine, sine, ex. There is no way I can connect them basically to the geometric series. So the question, what's the general theory? How can we do that? So that's the first questions we're going to address today. And the second part is the following. I'm going to write something and you have to tell me whether this makes sense. Suppose I take the function ln of x. You know the regular. Is it possible? That's the question addressed to you. Is it possible to write ln of x as a power series in x? Is it possible to write ln of x as something like that? Yes or no? And explain. Is it possible to write ln of x like that for x, for example, less than a certain number? Is this possible? Yes or no? What do you think? I'll give you a minute to think about the questions before we start. Is this possible? Is there any issue with that? Something come to your mind when you see something like that? Maybe because we know e to the x. Are we going to learn e to the x again? No, actually, no. Keep thinking. Is this equality possible? When absolute x less than r, when x, it means when x between minus r and r. Is this possible to tell you that for every x between minus r and r, ln of x could be written as this sum for all x's in here? Is this make sense? Probably it's a bit hard question, but not very hard. Anybody can actually try to say why I am asking this question. I mean, that's the issue. Any other ideas? Okay, let me see if this can help. Let us say when I put 1 over minus 1 minus x, and I wrote it like this: 1 plus x squared plus x cubed, etc. And this is true for absolute x less than minus 1. And we said that this is true. What does this mean to us? It means if I take any number x between minus 1 and 1, any x, suppose I take x equal a half, any number x, And I plug it in this sum here, and I start adding those terms. That's really what it means. I should get exactly that. That's what this means. If I take anything between -1 and 1, I plug it here, and I compute those partial sums, I get 1 over 1 minus a half. So no matter what x is, we should have inequality. That's really what this means. So in particular, for example, if I take x to be 0, what should happen? If I plug in a 0 in here, in the sum, I get 1. Plug in 0 in here, I get 1. Means those should give me the same answer regardless what x is between -1 and 1. Now I go back to that. Is this possible? Anybody? Where an issue can occur? Where can we have a problem? All right. Anyone? Negative values. That's a very good point. Negative values. We can have an issue. What else? You're on the right track, Sarah. -0. Absolutely. Is this possible? And my answer is absolutely not. Because as now Sarah figured out, if I put x equals 0 here, if this is possible, it means those should be equal to each other for all values of x between here and here. But this is absolute nonsense, because if I put 0 here, let us say, I will get C0. This is not defined. It doesn't make any sense whatsoever. Ln of 0 doesn't make sense. If I put any negative value here, it may make sense. There is no way to put a negative value. So I cannot write Ln of x as a power series in x for x between -r and r. So the question is, how can I write Ln as a power series? And the answer will be, I cannot write it as a power series in x. It means I cannot have an x in here. What I can have is the following. But I'm going to be able to prove that I can write Ln of x as a power series, but in the following sense. Not in x, but in what we call x minus a. It means instead of x, I can have a, where a is different from 0. And that's where we studied power series in x minus a. So I will be able to write Ln of x as a power series, but those will not be x, they will be x minus something, minus something, minus something. And this something has, the a has to be different from 0. And this is one place where we're going to be using also the power series in x minus a, not in x as well. So we're going to use them when my original function is not defined at 0. And then we can write them as polynomial, but instead of x, we're going to write them x minus a, like x minus 1, x minus 2, and so on and so forth. So, two things we're going to see today. First, how to represent function that we cannot relate to geometric series by a power series, and how we can represent them not only in x, because sometimes I can't do them in terms of x. How can we represent them in x minus a, where a could be basically any number as long as my original function is defined at this point, as well as its derivative. So I'm going to state the first theorem of today, and we're going to work with them. So this is the first idea. So in this section, we're going to learn how to represent most of the functions that we are familiar with in calculus. And I mean it. What are the most familiar functions we are familiar with? Ex, cosine x, tangent x. Those are the functions we're familiar with as a power series. So we're going to work with something we actually know. Now, the theorem below will do the following. The theorem below is going to find a relationship between the coefficients of the power series, the C0, and the function itself. So the theorem below will tell us how to find the coefficients of the power series of the function. So far, the only way we found the coefficient is by tricks. 1 over 1 plus x, I substituted x for minus x. 1 over 1 plus x squared, I substituted x squared for x. So everything I did so far is I started geometric series and I played games to be able to get to my power series. What this section is telling us, if you cannot play those games, which are going to be crucial, as you will realize very soon, if you cannot play those games and you want to write a function as a power series, what are they? How are those coefficients related to the function itself? So this is my first theorem of the day. I'm going to be the most crucial theorem. It tells me the following. Suppose I have a function and I wrote it as a power series in x minus a, because in general, we will be able to write it in x minus a. Suppose I wrote a function like this. The question is, what is C0, C1, C2 in terms of the function itself? What's the relationship between the coefficients here and the function itself? And the theorem tells me the following. If I can write it like this, then C0 is the value of the function at zero. Sorry, the value of the function at a. That's going to be the relationship. C1 is going to be the derivative of the function at a. So I'm building the relationship between the coefficients and the function. C2 is going to be the second derivative at a divided by 2 factorial. C3 is going to be the third derivative of the function divided by 3 factorial. And in general, Cn, it means the coefficient of x minus a to the n is going to be the nth derivative of at the point a divided by n factorial, where this notation, f parenthesis n closed a, means the nth derivative of f at the point a. So I'm going to read the theorem again because it's going to be crucial. It tells me that if you have a function, if you can write it as a power series, and you wrote a lot as power series in x, we never wrote in x minus a, but we're going to be doing this. So if you write as a power series, this theorem is telling me what's the connection between those coefficients and the function. Is what is C0 as far as the function is concerned? So far I was playing games. This tells me exactly what they are. They are telling me that this is the function at a. C1 is the derivative at a. C2 is not the derivative. It's the second derivative at a over 2 factorial. C3, the third derivative at a over 3 factorial. Remember, those are numbers. They don't depend on x, so they are fixed numbers. And Cn is the nth derivative at a over n factorial. Before I show you where this comes from, it means where those coefficients comes from, I'm going to work up an example. And the example I'm going to work out, so I will show you and I'll write it at the same. I'm going to take the following function, 1 over 1 minus 2x. And my question to you, do we know how to write f as a power series in x? Have we seen this problem before? Yes or no? Yes, we've seen it a lot. So if I take this function, 1 over 1 minus 2x, we've seen how to write it as a power series in x. In x, not x minus a, because that's the only thing we've seen so far. And let's remember, how did we do it? We started with 1 over 1 minus x. What did we do? We plugged in 2x for x. So we did the following. So from previous section, we know that 1 over 1 minus 2x equal. Remember how we did that? Of course you do. We took your exam 2 days ago. We started with 1 over 1 minus x, which is 1 plus x squared. And to get to 1 minus 2x, what did we do? We plugged in 2x for x, 2x for that. So this is going to give me 1 plus, instead of x is 2x, plus, instead of x is 2 square x squared, plus 2 cube x cubed to the power 4 plus so on. Okay, so what is the C0 in this scenario? C0 is the constant term. So far, I'm talking about something we know. C1 is the coefficient of x. So C1 is 2. What is C2? Quickly, I want your answers on chat, because I want you to know exactly what. C2, coefficient of x squared, that's a fixed number. C3, coefficient of x cubed, which is in my picture here, it's 8. C4 coefficient of x4 2 to the 4. So that's exactly what we know. So that's what C0, C1, C2. Now what I'm going to do, we're gonna get, so we got those coefficients basically by substituting to x for x in the power series of 1 minus x. Now I'm gonna do the following. I am gonna compute those coefficients again by using the theorem. And in my case, my A is 0. What I'm gonna think about now, and now this I'm gonna work it out in front of you. The theorem tells me if you can write the function as a power series, which is 1 over 1 minus 2x I can do, then another way to find the coefficient is by using this formula. So now I'm gonna take the function 1 over 1 minus 2x, and I'm gonna compute again the coefficient using this formula, so that I can convince you that the form, regardless how we find the coefficient, they are always the same number. So we're gonna do that again by finding the formula. What does this formula tell me? So let me apply it for you. I'm gonna take my function f to be 1 over 1 minus 2x. And I was able to write it. Now I'm gonna write it again by using those coefficients. So what is C0 according to this formula? It's the value of the function at A. So in my scenario here, because I want to write them as power series in x, it means my A is 0. So this formula tells me that C0 is the value of the function at 0. So the value of the function at 0 is equal to 1. So C0 is 1, which is what we got before. Now, what is C2? This formula tells me that C2 is the derivative at 0, basically over 1 factorial. But what's the derivative at 0? So this is my f. I'm going to find its derivative. What is the derivative? I'm going to take this function, raise it to the power 1, because that's the easiest way to find the derivative. And what do I get? What's the derivative of that? It's minus the power 1 minus 2x to the minus 2 times the derivative of what's inside, which is minus 2. It means my derivative is 2 times 1 minus 2x to the minus 2. This theorem tells me, that C1 is the derivative at 0. That's the derivative at 0. It means I plug in 0 in here, divided by 1, which is equal to 2. So according to this formula, C1 equal to 2, which is absolutely exactly what we had by writing it this way. So I'm trying to now show you that use this formula is the same thing as what we've done so far. So that's exactly what we got, C1 equal to 2. Now I'm gonna find C2 by computing using the formula again. Okay. What does C2 tells me? C2 is the second derivative at 0 over 2 factorial. So to find C2, I'm going to find the second derivative of x. But the second derivative of x is 2 times minus 2, minus 4, 1 minus 2x to the minus 3 times the derivative of what's inside, which is minus 2. It means minus minus plus 8 times that. So what's the second derivative at 0? I plug in 0 here, I get 8 over 2 factorial, which is equal to 4. Again, this coincides with what we found by manipulating the geometric series, C2 equal to 4. So one more time. So what is C3 according to this formula? So I compute the third derivative. Now this is minus 3 times 8 minus 24. 1 minus 2x times the derivative of what's inside. This is going to give me 48 times that. So now the formula tells me that C3 is the third derivative at 0 over 3 factorial. If I plug in 0 for x, I'm going to get 48 over 3 factorial. 3 factorial is 6. So this is going to give me 48 over 6, which is 8. So the theorem tells me T3 equal to 8, and that's exactly what we got previously. We got also T3 equal to 8. So what this really tells me that the coefficients are the same as the one we found for f of x by manipulating the power series of 1 over 1 minus x. It means my theorem actually holds. It means that the relationship, that the coefficients, this tells me the following, that when I take my functions, 1 over 1 minus 2x, and I write it as 1 plus 2x plus 2 squared plus 2 cube x cubed plus this and so on, then those coefficients, and this is my function f of x, they are not arbitrary coefficients. Those are related to function by the following. The first coefficient is the function at 0. This one is the value of the derivative at 0 over 1 factorial. This is the second derivative at 0 over 2 factorial. This, the third derivative at 0 over 3 factorial. And this, the fourth derivative at 0 over 4 factorial. So those coefficients that we get are not arbitrary. They are really given by a very specific formula, which is this formula. Okay, and this gives us a tool to find the power series basically of any functions, because now I have a formula for the coefficient themselves. I'm not manipulating anymore. The theorem is actually giving me a formula for the coefficient themselves. Now, before I go on and we start working with this, let me a little bit give you an idea where those magical CNs are coming from. So I'm going to spend a few minutes, hopefully not more, because the proof is clear in the book. So I'm going to spend a few minutes to tell you where those coming from. So help me out. The idea is this. Suppose I have a function f. So you should know where it is coming from. And I wrote it as C0 plus C1x minus a plus C2x minus a squared plus C3x minus a. Suppose I wrote a function like this. I'm not going to go more than that. Okay? Suppose I wrote it. And I'm trying to find the relationship between those coefficients and the function. So I can generalize the idea of a power series. What are they? So the theorem tells me what are they. I'm trying to explain a little bit where the theorem coming from. If those are equal to each other, it means they should be equal at A. So I'm going to plug in. So plug x equal to A in both sides. What do we get? I plug in A here, I get f of A. If I plug in A in here, what do I get? Quickly. If I plug in A in here, what do I get? X equal A, 0, 0, 0, 0. I get C0. That's the first term. So this C0, every time you write something as a power series, this first term is the actual value of the function at A. Now let's see where C1 is coming from. Now, last lecture, we saw that we can differentiate a power series term by term. So I'm going to differentiate this, f prime of x. That's going to give C0 is a constant, derivative 0. We're going to get C1 plus 2 C2 x minus a. I'm differentiating term by term. Plus 3 C3 x minus a squared. Plus 4 C4 x minus a to the power 3 plus etc. So the idea is to tell you where those C's are coming from. Again, now I'm going to plug x equal to a in both sides. So I'm going to plug a here and a here. What do I get? If I plug a here, I get the derivative at a. I put in a here, 0, 0, 0 equal to C1. I got C1. Now, I'm going to get C2. Ideas? Who wanna tell me what I'm gonna do next? Quick. I'm gonna take this and differentiate it. Take the derivative again. So I'm gonna compute the second derivative. And it's gonna give me, C1 is a constant out the picture. It's gonna give me 2 C2 x minus a plus 2 times 3, but I'm not gonna put it 2 times 3 now. I'm gonna write it this way. I will not compute it. X minus a, sorry. Okay, this go. My apology. Because the derivative of x minus a is 1. Plus, again, I'm not gonna write 3 times 4, 12. I'm gonna keep it the way it is. C4 x minus a squared plus so on. Again, I'm gonna plug a both sides. And I'm gonna get the second derivative at a is 2 times C2, and the rest is 0. And so this is gonna give me that C2, the second is the second derivative at a over 2. I got a formula for C2. And now I guess the picture is clear. I'm gonna get differentiate again, and that's really where those coefficients are coming from. So the third derivative, and I promise you I'll stop after that, is equal to the derivative of 2C2, that's a constant. Here I'm gonna get 2 times 3. Derivative of x minus 1, a is a constant. The derivative of that is 1. Plus, what's the derivative here? It's a 2 times the 3 times the 4 times C4 x minus a, and etc. I plug in x equal to a both sides. What I'm gonna get? The third derivative at a will be equal to 2 times 3 C3 plus the rest is 0. So C3, and that's where the factorial is gonna come. It's gonna be the third derivative at a over 2 times 3, which is 3 factorial. And you know, I'm gonna keep going. The fourth derivative, this will go, I'm gonna have 2 times 3 times 4 plus bunch of terms, and C4 will be the fourth derivative at a divided by 2 times 3 times 4, which is the 4 factorial. So that's really where the theorem is coming from. It's not magical, it's just by differentiating over and over. Okay, so now we established the most important idea, which is the relationship between the coefficient and the function, which tells me that if a function, I can write it as a power series, I know what the coefficients are. So now this would lead me to the following definition. Here. So what we have so far, if I have a function and I can write it as a power series, the theorem tells me that those coefficients are given by this formula. So if we substitute the nth derivative a over n factorial for the Cn, the power series become f of x become f of a, I'm going to substitute this for C0, f prime of a, x minus a, f double prime of a, 2 factorial, x minus a squared, plus the third derivative of 3 factorial, plus so on. And in sigma notation, we write this as sigma n equals 0 to infinity, f to the n a n factorial times x minus a factorial. Now let me talk a little bit about this notation. F0 of a basically means the actual value of the function at a. So for this notation to make sense, if n is 0, this means the function itself at a. This series is called the Taylor series expansion of f at the point a. So the idea is, if you can have a function, if you can write it as a power series, these are the coefficients. So we know what the coefficients are. So now we're going to call this series f of a plus f prime of a plus etc. This will be called the Taylor series expansion of the function. This is the series which helped me to find the power series representation of almost any function I want. Now, if A is 0, if A equal to 0, which is what we've done so far, means if I put in here 0, then the sequence, the expression become f at 0 plus f prime at 0, x, f double prime at 0 over 2 factorial plus etc. So in sigma notation is the nth derivative at 0 over n factorial. This one is called the Maclaurin series of f. In other words, Maclaurin series is Taylor series where a equal to 0. So the question is that why they have two names? They have two names just because they want to give credit for two different people, Taylor and Maclaurin. That's the reason we have two names for the same thing. So Maclaurin is the same as Taylor, but instead of A, we have A is equal to 0. And the only reason we have two names is one reason: give credit to two different people, for Taylor and Maclaurin, for working on those ideas. That's why we have two different. So before we start the computational part, and I finalize this one last theorem, I promise you, and then we're going to be doing practice problems. Okay, the theorem below holds for most of the function we encounter in calculus. It means most of the function we're going to work with in calculus, not every possible function, the following will work. If a function f is infinitely differentiable, what does it mean? It means the value of the function near a point A. What does infinitely differentiable? It means the first derivative exists, the second derivative exists, the third derivative exists, the function exists, the 100th derivative exists. If you have a function that have all these properties, then this function is actually equal to its Taylor series at A. And the equality holds for all values of x where the Taylor series converge. So what the theorem tells you is that for most of the functions that we're familiar with, not every possible function that exists, the one that we're going to work with in this class, the sine, the cosine, the log, the arctangent, those functions, we can write them as a power series in x minus a. And the formula for this power series is the Taylor series. This is the formula that's going to help me write this as a power series. So now we're going to start the practice part because the theory, take a toll on us. Now we're going to start practicing a little bit. So example number 1 is find the Maclaurin series of the function f of x equal e to the x, which is I did before the exam, but now we're going to do it using the new formulas we have. Find the Maclaurin series of the function f of x equal ex and find its radius of convergence. Okay, I'm going to redo this in front of you. It's already on your notes, but we're going to do it together so we practice how to proceed. So I'm going to find the Maclaurin f of x equal e to the x. That's the easy one. So this means I want to write this function as a polynomial of infinite degree. That's really what we are doing. I'm going to apply the formula verbatim. So I write the formula in the Taylor Maclaurin. It means a equal to 0. So the formula tells me that the function e to the x is f of 0 plus f prime x. F double prime at 0, you have memory of this. You have to almost memorize. And if you had a regular classroom, I would have forced you to memorize it. Now I don't have control. Plus, etc. So to write e to the x as a power series, I need to find f of 0. I need f prime. I need f double prime. I need the third derivative. I need the fourth derivative. So it's not really easy. I have to compute tons of derivatives to be able basically to write this function. But let's do it. This is a very easy function. So let us do that. So f of x is e to the x. So f of 0 is e to the 0, which is 1. Okay? Now, I want to find the coefficient of x. I need the derivative. But what's f prime? Is again e to the x. It means f prime at 0 is 1. What's the second derivative? Again, e to the x. That's why it's a very easy function. It means its second derivative is also equal to 1. Do I need to keep going, or I know the pattern? You know the pattern? Absolutely. All the derivatives for any order. So in general, if I compute the derivative of any order, so when I put fn, so if n is 2, it means second derivative. If n is 3, that means third derivative. N is 4, the fourth derivative. N is 100 means the 100th derivative. It means all of them are 1. So what's going to be the power series of e to the x? It's going to be the following. F of 0, 1. F prime of 0, which is 1 times x, plus. But now things change. It's the second derivative over 2 factorial. So it's not anymore the second derivative. It's the second derivative over 2 factorial x squared. The third derivative over 3 factorial x cubed. The fourth over 4 factorial x squared, etc., etc. So in sigma notation, this is going to be sigma x to the n over n factorial. N equals 0 to infinity. And here I remind you that 0 factorial is equal to 1. Now, when does this equality hold? So e to the x could be written as a power series like this, but for which value of x? The theorem tells me that the equality holds for all values of x where the Taylor series converge. So we have equality for every x where this one makes sense. So to be able to know where we have equality, I'm going to ask the following. For which value of x does the series converge? So we have to go back and ask ourselves. This is a power series. When does this converge? Okay, we do what we've done before. So now convergence, radius of convergence. Okay, at this stage, I'm going to do what we've done before, what we've done every time. So what do I have to do? I'm going to pick up an and find it. An is xn over n factorial. I'm going to compute the limit of an plus 1 over an. I've done this several times. That's why I'm reading this. So I get x to the n plus 1 over n plus 1 factorial times x factorial over the absolute value of x to the n. X to the n plus 1 over x to the n give me the x. N factorial over this give me n plus 1. This is equal to 0, which is less than 1 for all x. Which means that the series sigma xn over n factorial will converge regardless what x is. And now we have one of the most important formulas, most of the most important Taylor series or Maclaurin series we will encounter, which is e to the x. So e to the x is 1 plus x squared over 2 factorial plus x cubed, and this equality holds for regardless what the value of x is. So whatever x is, this equality will hold. So for example, so what I am telling you now is that no matter what x is, e to the x is actually equal to this, no matter what x is. Plus so on. So what I'm telling you is the following. If I put x1 here, those are equal. So it means if I take x to be 1, and I put x1 in this expression, those two are equal. It means if I start adding those sums, adding them, physically adding those partial sum will be close to e to the 1, which is 2.71. So the exercise for you is take those and start adding them. You should get exactly e. But it's not only true for x equal to 1, but I'm telling you that if you put 2 in here, and you plug in 2 for x, it means 2 squared over 2 factorial, 2 cubed over 3 factorial. And again, you compute those partial sums. You start computing them, you realize that those partial sums are going to get close to E squared. It means 2.714 square, which is almost 7 point something. So that's really what it means. So if you want to estimate E squared, you don't know how to estimate it, you don't know what the value of E squared is, it's not a big deal. You write those and you start computing the partial sums. When you realize that your partial sums are getting close to a number, that will be E squared. So I can now estimate E to any power by actually using that power series. And a lot of time people define E, the definition they give to E to the power 1, instead of giving you this approximation, they define E as being the sum 1 over n factorial. Means we defined E to be the following partial sum, the following infinite series. Okay. All right, now let us practice the theorem again. And now I'm going to find the power series, the Maclaurin series of the function f of x equal, I don't know, sine x, let us say. So let's take f of x equals sine x, and I'm going to write the sine as a power series. It means we're going to write the sine as a polynomial. So we're going to do the same for f of x equal sine x, and write it as a series. So the same, and I'm going to ask the Maclaurin. And my last example is not Maclaurin, it's something else. Maclaurin, it means my A is equal to 0. That's crucial. So the theorem tells me that I can write sine x as f of 0 plus f prime at 0 x, f double prime at 0 over 2 factorial, x squared plus the third over 3 factorial, the fourth over 4 factorial, x cubed, x4, plus so on. Okay, we'll write the sigma notation when I compute all those derivatives. So now to find s derivative sine x, I need to find those derivatives. So that's why it's not easy always to use the theorem, because I have tons of derivatives to compute. Well, let's do that. So I have f of x equals sine x. And what is f of 0? Is the sine of 0, which is 0. Now I need f prime as 0, so I need to compute f prime. It's cosine of x. So f prime at 0 is the derivative, cosine of 0. Cosine of 0 is 1. Now I need the second, so I'll be patient enough, compute the second derivative. The second derivative of cosine is minus sign. So my second derivative here is going to be minus the sine of 0, which is equal to 0. And I want you to stop me when you are bored. Is that clear? When you're bored, stop me. Tell me you don't need to compute anymore. Now, what's the third derivative at x? Derivative of sine is cosine, so that's minus cosine of x. So at 0 is minus 1. Now, what's the fourth derivative? Sine. So the fourth derivative at 0 is equal to 0. Do you want me to keep going? What's happening right now? It's fine. Okay, thanks, Adam. Because what's happening right now? We are basically recycling the derivative. It's going to repeat from there, because the fifth derivative is going to be the cosine, then minus sine and minus cosine. So let us make sure, use this repetition and write the power series. So how are we going to write the power series of sine? F of 0, 0, plus f prime at 0, which is 1 times x, plus the second derivative at 0, which is 0 over 2 factorial, which is 0, times x squared. Then the third derivative is going to become minus 1 over 3 factorial x cubed. And then the fourth derivative, which is 0, x4. And then by recycling, I'm going to go back to here. So it's going to be 1 over, sorry, plus 1 over 5 factorial x5, and so on and so forth. So let me rewrite it in a nice way because I don't want zeros that make things confusing. So the sign is going to be x minus 1 over 3 factorial x cubed plus 1 over 5 factorial x5 minus 1 over 7 factorial x7, and so on and so forth. So in sigma notation, because we should know how to write sign in sigma notation. Okay, let's do it in sigma notation. And let us watch what's happening here in sigma notation. What kind of power are left? What kind of power? Odd power. Very good. How can I rewrite an odd number? So odd number, how can I write it? Because I need to write this. How can I write an odd number? Before I ask you an odd number, how do we write even numbers? So odd numbers are always an even number plus 1. Okay, even number. What's the general form of an even number? So even numbers are 2, 4, 6, 8, right? So every even number is 2 times a number. 2 is 2 times 1. 4 is 2 times 2. 6, 2 times 3. So odd are always an even plus 1. So that's how we write every possible odd numbers. So this is going to help me to figure out how to write those. So every power here is to n odd. So every power here is to n plus 1 because it's an odd number. And my n is going to start. So my first odd is 0 to infinity. So I'm picking up the powers. At 0, I have 1. And then at 1, I have 3, and so on. Now, what about the coefficients? The coefficients are the denominator, we know it, is to n plus 1 factorial. Now I have problem with the numerator. The numerator is a minus 1 because it's alternating to a certain power. I'm going to put n and check if n will do. Okay, so if n is 0 minus 1 to the 0, it's a positive number. N is 1, I'm giving minus 1 over 3 factorial. So and this is going to give me the power series of the sum. This tells me that the sine x, this is actually nothing more than the sum of terms that looks like this. So it only involves the odd power. And this works for all x. It means that if I take this series and find the values of x where this series converge, I realize it's gonna converge for every possible value of x. So again, as before, if I put 1 here, sine of 1, I put 1 here, those are, and start computing partial sums, I will get the sine of 1. So whatever value I put for sine, here, 1, 2, 3, pi over 2, pi over 4, and I plug it into the expression of the series, the partial sum in the series will converge to exactly the value of sine x. So sine x is inevitably a polynomial of infinite degree. All right, the last problem I will do, because all those examples I did, which are really basically to memorize, are Maclaurin. So my last example is, okay, I'm gonna do a little bit Taylor for a simple function, and I'm only gonna find the first term just to make the problem easy. So I forgot which one I gave you on my notes. So guys, look at the problem I gave on my note, but let me take something else. Suppose I tell you f of x equal ln of x, and my question is the following. Find the first, let us say, 4 terms of the Taylor series of f at the point a equal to 1. So I don't want all of it because I don't have time for all of it, but I want the first 4 terms of the Taylor series. But first I'm going to write it. So it means what I want. This is my f of x. Since I want only the first 4 terms, I'm not going to write equality because it's not equality. Because I'm only using the first 4 terms. It's going to be equal to f at 1. A equal to 1, it means I have to express things at 1, plus f prime at 1 times x minus 1, plus f double prime at 1 x minus 1 squared, plus, so I only want the first 3 terms, sorry, that's 2 factorial, 3 factorial x minus 1 to the power 3. So only those terms, okay? So, but I still have to compute a lot. F prime, f double prime, and the third derivative. So let us do that. So this is my f of x equal ln of x. Actually, I'm going to add the first non-zero terms, and there is a reason, okay? So what is f of 1? ln of 1, which is 0. So this is gone. So I may need to add the 4th derivative at 1. Very good. Now I need f prime. So now the tedious work of computing derivative. So that's the derivative. It means the derivative at 1 is 1. I found the derivative at 1. Now the second derivative. So I need to compute the second derivative. Now the easiest way, because we're going to compute tons of derivative, is to rewrite this x to the minus 1. This makes my problem easy. So that's going to be minus 1 x to the minus 2. So my second derivative at 1 is minus 1. Now I need my third derivative. So as I repeat, it is tedious. It's 2 minus 1 x to the minus 3. So my third derivative is going to be 2 at 1. At 1 is crucial. Finally, my fourth derivative, 2 times minus 3 to the minus 4. So my fourth derivative at 1 is equal to minus 6. Now I'm going to put the whole thing into one expression and we finalize it. So what are the first 4 terms of ln of x? Let's put them out. I only want the first non-zero term, but I ended up with f of 1, 0. That's why I pushed it to the 4th derivative. So this tells me that ln of x, we'll talk more about this notation very soon, is f of 1, it's 0, plus f prime of 1 is 1 times x minus 1, plus the second derivative, it's minus 1 over 2 factorial x minus 1 squared. So these are the terms. Now the third derivative. The third derivative was 2 over 3 factorial x minus 1 to the power 3, plus the fourth derivative was minus 6 over 4 factorial x minus 1 to the power 4. And the power series itself has more terms, but we're only interested in the first. So actually, I'm going to change it to equal to make it easy for us. So finally, it's going to be equal to x minus 1 minus 1 over 2 factorial x minus 1 squared, plus 2 over 3 factorial is how much? 3 factorial is 2 times 3 basically. So it's going to give me 1 over 3 x minus 1 to the power 3, plus 4 factorial is basically 2 times 3 times 4. 2 times 3 is 6, and 6 cancel out. So I'm going to erase this plus here, and I'm going to get minus 1 over 4x minus 1 to the power 4. So this gives me the first non-zero term of the Taylor series of the function ln of x at x equal to 1. And the idea is we will be able to approximate ln of x by this polynomial. But this polynomial is in x minus a. So when I'm going to find its radius of convergence, it's going to be actually x minus 1. If we do the math, it's going to be x minus 1 less than 1. So this will hold as long as x is x minus 1 between 1 and minus 1. It means it's going to hold for x between 0 and 2. So this series is going to hold for x between 0 and 2. And now things make a little bit more sense, because for x between 0 and 2, ln of x makes sense, which it did not make sense if I did not have x minus 1. If I had x, it was nonsense. So this time, this will make ln of x make sense, and this series will converge as long as x between 0 and 2. And the reason being, if I kept going, the general term is going to be that. And so on and so forth. Okay, so that's it for today. So what we did today is actually find a general formula for how to find the power series of most of the functions that we're familiar with. So we just found a formula for it. So tomorrow I said, okay, what we've learned, is it a waste of time or is it necessary? And of course, it's going to be necessary, what we've learned before, because the way we're going to do now is that now I have a formula for any function, but if I have a more complicated function, sometimes I have e to the, like even if I have x times e to the x, and I'm going to ask to find the power series of that, using the formula that we've learned today is going to be really complicated. Using what we've learned last time is going to be easier to find the power series of those type of functions. And this is what we're going to look at it tomorrow. All right. Any question, guys? I know I talked all the hour today, but because it's a new material, do you guys have any questions? Anything? Okay, then please do the homework, and see you tomorrow. Bye-bye, guys.